Okay, welcome to the second part of the carbon NMR discussions. We talked about why it's C13, what are the special features of carbon-13 NMR, number of peaks, chemical shifts, and the intensity of the peaks, and so on and so forth. We also talked about the spin-spin splitting pattern in carbon-13 NMR. We talked about homonuclear coupling, that is carbon-13 NMR coupling is not quite possible because of the low abundance and the remote chances that a carbon-13 nucleus would have another carbon-13 nucleus adjacent to it. Okay, because the carbon-13 is only 1%. The natural abundance of carbon-13 is only 1%. So only 1 in 10,000 molecules would have carbon-13 beside it. Then that's when it would couple, but that coupling would be going into the baseline or into the noise, so we will not see that minute residual coupling, right? So excuse me. Then we looked at proton C13 coupling. We looked at the simple spectra, and that's quite useful because depending upon the number of attached hydrogens, for example, this carbon has 3 hydrogens attached to it, so it's a quartet. This carbon has only 1 hydrogen, so this carbon is doublet in C13 NMR. This is the effect of hydrogens, or the coupling of hydrogens with that of C13, right? This is called heteronuclear coupling, proton C13 coupling. In a complicated molecule such as cholesterol, the spectrum becomes pretty noisy and pretty overlapping, and the advantages of this spectrum, this off-resonance spectrum, it's kind of overtaken by the complexity that you see here. There are some advantages in the sense that we can deduce the information about the nature of carbons, or the primary or the secondary and tertiary can be gleaned into from looking at the off-resonance spectrum, but the advantages are pretty small compared to the complexity it generates. So how do we assign the types of carbons? That's something discussions that we are going to focus on. However, so there came along some technique that decouples the proton, and as a result, the sensitivity of the carbon-13 signals has been increased, and also that the spectrum is pretty much simplified now. The complexity has been taken off because you are nullifying the effects of the proton on carbon-13. Otherwise, there are no local magnetic fields, and therefore there is no spin splitting. And as a result, each one of the peaks are singlets, and each singlet corresponds to one chemically non-equivalent carbon, right? So if you have 30 peaks here, that number corresponds to the 30 carbons of cholesterol, but we don't know what types of carbons are these. Are they methylenes, are they methyls, are they methynes, and are they quaternary, right? So that information has been lost in decoupled spectrum. This is broadband decoupled spectrum. This is off-resonance spectrum. Off-resonance spectrum have had its advantages. It has advantages, but that's been taken off in this single line spectrum, broadband C13 NMR, right? So how do we get that information back? Let's say we need it. We don't have any other way to assign these carbons otherwise. So the scientists have come up with various techniques. These are called edited C13 NMRs. There are quite a few of them. They can be broadly classified into 2 types, apt and DEPT. apt is an acronym for attached proton test. DEPT is an acronym for distortionless enhancement by polarization transfer. This is pretty technical jargon. At your level, at undergrad level, I don't think you need to know all this terminology, but if you are interested, we do teach an advanced spectroscopy class in our department, so you can take that class. And again, we have different types of depths. depending upon the processing. You remember, this is editing. It's like shooting your movie and you sit down and edit as to what you need. Probably you can delete some information, or you can add some information, or you can modify some information using the technology. The same is true here. You are turning on, turning off some things in the instrument, and so that you're writing your pulses, the delays, the relaxation delays, things like that. And as a result, you can collect the data that you want selectively. You can only look at some part of the window where you can see only one type of carbons rather than the other type of carbons. For example, you can only focus on methylenes or methynes or methyls. So that's called editing of the C13NMR, right? So that's the reason why these techniques are called edited C13NMR spectroscopic tools, right? So APT is also one type of C13NMR. That's what you should be remembering. We are not out of carbon NMR. We are in carbon NMR, the broad topic. In that we are learning various techniques. One of the technique was off resonance spectrum. It's useful to some certain extent. However, it complicates, so we went for decoupled spectrum. That's broadband decoupled single line C13NMR. It has its advantages, but we lose some information there. We don't know what type of carbons are there, so we need to have special techniques. For that, there came along some techniques such as APT and DEPT. And APT is attached proton test, DEPT is distortionless enhancement by polarization transfer. You are transferring some polarization and there is no distortion, and it is enhancing something. So all these terms are kind of self-explanatory, but you don't have to worry about it if it is too much technical at your level. So let's look at them as to how do they look. So without worrying about the instrumentation part, we would just take the advantage of the spectrum that is collected by these. Let's say we have instrumentation guy who helps us with the collection of the data. Okay, so this is slide which shows three types of NMRs here. This is a phosphonic acid derivative, and as you can see, there are aromatic carbons and there are aliphatic carbons. And there is phosphorus, anyhow. Phosphorus has its own NMR, P31. That will be an advanced topic at your level again, so you don't have to worry about that. There will be coupling between phosphorus and this carbon, but again that is kind of in a different window of the frequency, so we can nullify that as well. We don't have to worry about that in carbon NMR right now, as we see here. So there's methane here. So there are different types of carbons. If you were to collect the single line normal decoupled C13 NMR, this is how it would look like. Everything is a singlet. You don't know which one is for what. If you ask me, when I can see the CH, maybe the CH is overlapping somewhere here, or where is that CH, right? So that's kind of, maybe it's somewhere here because it's attached to two electronegative atoms, right? So pretty much difficult to assign the types of carbons. We can take a look at the electronegative atoms that are attached to, and then probably we can assign the chemical shifts to a certain extent. But it would be good if we have a technique which can tell us these different types of carbons apart. Let's say we can surely pinpoint to methynes, methylenes and methyls, quaternary carbons. That would be valuable information, right? So there came along this technique called APT. In APT, what's happening is you see all the signals for all the carbons, just that some are positive, some are negative. If you consider this baseline as a 0 level, then some peaks are pointing upwards, those are called positive peaks. Some peaks are pointing downwards, those are called negative peaks. And this is the CDCl3 signal. This CDCl3 signal is pointing, this is the CDCl3 signal that's pointing downwards in APT, right? So what are the things that are pointing downwards, or what are the things that are seen as negative peaks in APT NMR? Methylenes are negative, quaternary carbons are negative, and methynes, this is methine and this is methyl, they are seen as positive peaks. So now I know as to which one is my methylene. This is methylene, so I can safely assign that to this carbon, and this is methyl, so that must be that methyl. And there are some quaternary peaks. There is one here, and there is another one here, so this must be these ipsocarbons, right? There is a symmetry here. So you see 1, 2, 3 peaks for this aromatic type. So out of those, these two are the the quaternary carbons, or the ones that do not have hydrogens, and they are pointing downwards, right? And depending upon the chemical shift, I can assign either to this or to this, these two peaks. However, app takes a lot of time, a lot of sample. It's as tedious as collecting single line broadband C13 NMR, and also the peaks are not as clean as you would see here. See, this is much taller and also taller, but it takes more time to collect the data in apt than it would take in any other C13 NMR. So that aspect has led scientists to do something more in the editing process, and they developed something called DEPT. In DEPT, there are different types of depths. In depth 135, I guess, depending upon the angle of the pulse, I think you can differentiate the carbons. The one thing is missing here. What is missing? In normal C13, you see all the carbons. The quaternaries are normally small and they are downfield. They have higher chemical shifts normally because they're either aromatic or quaternary. They have a lot of substituents, so they are small. They are downfield, deshielded. And their intensity is pretty small. That intensity is due to the relaxation time differences. The ones which have attached to hydrogens, they relax pretty faster. The carbons that do not have hydrogens attached to, such as quaternary carbons, relax slowly. So the intensity that the C13s produce would be small. Those peaks are not seen in depth. Whereas these are seen as negative peaks, the quaternary carbons are seen as negative peaks in apt, but in depth you are missing them. So if you have to know about your quaternary carbons, you cannot just run a depth. You have to run both. You have to run the normal C13 NMR, and then you have to collect depth 135 and then subtract this spectrum from this spectrum. Then you see what is missing. That missing must be quaternary carbons. And there are two types of peaks here also, the negative peaks and the positive peaks. Methynes and methyls give positive peaks, methylenes give negative peaks, and that's negative. So I know that that's methylene and that's methyl, and these are methynes, this methine, this methine. Do we have more methynes? No. So why do we have three peaks? 1, 2, 3. 1, 2. There's something, maybe there's some solvent in here probably. So that's one of the reasons. Anyhow, what is the summary of the discussion? Methyls and methynes go up in the depth 135. Methylenes go down as negative peaks, and apt shows all of them. Again, methyls and methynes give positive peaks, quaternary carbon and methylenes give negative peaks, and normal C13 NMR gives all the peaks. So depending upon the need, if you really bother about the type of carbons, you collect either depth or apt. Single line spectrum is not going to cut it for you. Okay, if you don't care, you can run the single line NMR spectroscope. I suggest sometimes to run just apt, because apt gives all the carbons, and some are positive and some are negative, so you don't lose any information. In depth, you lose some information about the quaternary carbons, but that itself is an information because you don't see them. In depth, there must be they are quaternary carbons. So, and then you know that methylenes are going down, methyls and methynes go up. So then there are different types of depths. As I said, apt has been overtaken by depth. Depth is pretty much easier to run than the apt. Okay, and it lets you determine the number of attached hydrogens. If there are two peaks that are negative, then you know that there are two methylenes, right? So you can differentiate between different types of carbons, whether it's primary, secondary, or tertiary, whether it's methyl, methyls, or methynes. Okay. So apt has been outdated now, and not many people run apt because now we have more sophisticated depth spectroscopy available. Okay, so in C13, in depth C13 NMR, a second transmitter irradiates the proton during the sequence, which affects the appearance of the C13 spectrum. doesn't quite take off all the effects of the hydrogen. In the decoupled broadband spectrum, you are nullifying all the effects of the hydrogen. You are not worried about, you're not even looking at hydrogen. Here you do kind of make use of that hydrogen presence, and then you use that to edit the normal information that would otherwise get in C13 NMR. So for example, in depth 135, you have advantage of differentiating between methylenes and methyls and methynes, right? Some C13 signals stay the same, they are positive. Some C13 signals disappear, they are quaternary. Some C13 signals are reversed or inverted, those are the negative peaks. That's pretty common across all the depth spectrum. There are three types of depth spectroscopy techniques that are available. For example, NMR spectroscopic techniques available. For example, depth 45 shows all the carbons, primary, secondary and tertiary carbons. Depth 90 shows only tertiary carbons. Depth 135 shows primary and tertiary carbons as positive peaks and secondary carbons as negative peaks. What is this 45 and 90 and 135? These are the pulses, angles, okay? So you don't have to worry about that right now. So just to remember, depth and apt are the techniques that we have developed to identify different types of carbons present in a given carbon compound, right? Normally carbon compounds, quite a few carbons, some of them are attached to 3 hydrogens, some of them are attached to 2 hydrogens, some of them are attached to 1 hydrogen, some to none. So depending on that, we differentiate all these carbons as quaternary, tertiary, secondary and primary, right? So if you do the broadband decoupled spectrum, all of them are shown as positive peaks. If you do depth 90, you only see those which have been attached to 1 hydrogen. That means you can only see methynes in depth 90. In depth 135, you see these two as positive and CH2 as negative. In depth 45, you see all of them as positive peaks, except for the quaternary carbon. Okay. So if you run a depth 135 and if you subtract this from this, you can identify the missing quaternary carbons. So you can get the information of the quaternary. If you want to just see at the methynes, you can simply run depth 90. You don't need to run this or this. You don't need to have broadband decoupled spectrum, and you don't have to have depth 135 spectrum. You just go directly, place your sample and set your experiment to pulse and to collect the data for depth 90. All the experiments are set up in an NMR instrument. Without knowing the instrumentation part, you can just select the experiment that you want. If you want to learn, if you want to become a spectroscopic person or scientist, you can learn them in much more detail. Anyhow, if you want to look at the negative peaks, if you want to look at the methylene peaks, you can just run 135, depth 135, and then look at the negative peaks. That would tell you the number of methylenes. This methylene can be any methylene, right? That has 2 hydrogens. We'll talk about what are different types of methylenes. CS3, you can just run depth CH and subtract this spectrum from this positive side of the spectrum, and then you know that the methyls are missing in here. So if a peak is present in depth 90 as well as depth 135 on the positive side, that must be CH. So whatever is missing here, and that is present on the positive side of depth 135, and that's methyl. Okay, so you can deduce different types of carbons by running different types of depths. That's a summary of the slide. We'll look at some examples, so you would appreciate how it helps organic chemists. For example, this is a compound which is phenone, butylphenone. It has 4 aliphatic carbons, so you have 4 peaks for them, and you have a carbonyl. So that's the carbonyl, and it's an aromatic ketone. And you have 1, 2, 3 different types of aromatic carbons. So you have 3 peaks for that. One of them is quaternary, so that is smaller. Okay, so pretty much you don't need depth all the time. But if you have a simple compound, if you have complex compound, then you need to take. If you have an unknown compound, then you need to take. Now I know the structure. I know the atoms attached to each one of them, so I can probably go by chemical shifts and I can assign. But out of these three methylenes, you're not sure which one is which. We only know that these are methylenes because the chemical shifts are much higher than methyls. Okay, and these are aromatic. And if you run the depth of that, something is gone, right? We had a carbonyl peak around 200, but that is missing here. So what that is missing is a carbonyl. So there is no doubt about that. That is carbonyl peak. So we can assign. And there was some other peak here from this carbon. That's also gone missing. So you can go backward, see that that is missing. So the quaternary carbons do not show up in depth 135. Okay. Methynes and methyls show as positive peaks. So we have one methyl and two or three methynes, because 1, 2, 3, and that's seen here. Again, each one of them corresponds to one type of carbon, just that the intensity is not same. That's something you should always remember. The intensity cannot be integrated, but we have two of them are coming at the same chemical shift. That's why this is double the intense as this one. We have two of them here, so there's almost double, but we don't quite integrate it. We only look at the number of different types of carbons in carbon-13 NMR. Okay, the integration is not as important as it is in hydrogen NMR or proton NMR. There are three methylenes, and these methylenes are here, and there are three different chemical shifts. One of them is adjacent to carbonyl, so that is pretty downfield compared to the rest of the two. Okay, in other words, this is de-shielded compared to these two. Okay, any questions? If not, we'll move forward. If you have questions, please revise the slides or stop by and see me. Okay, so what is unaffected in the depth? These signals were as before. They were positive side in the previous NMR, and they are going upwards even in the depth. So, or you can say that the CH and CH3 are positive, carbonyl, quaternary carbon and carbonyl carbon are missing, methylenes are inverted or negative peaks. Okay, so do you all understand what it's about? Depth 135. It's all about differentiating different types of carbons, right? We have a compound here which is kind of an alkene containing alcohol. It has different types of carbons. We have methyls, methylenes, methynes, and again a quaternary carbon. How many carbons do we expect? Are these methyls different from one another? Yes, because you have double bond. This methyl is cis to this group, whereas this methyl is trans to this group, and as a result this has a different chemical shift, different chemical properties than this one. It's magnetically different, so we expect 8 peaks for this compound, and one is attached to oxygen, so that is kind of around 60, right, because it's attached to oxygen, and there is allylic carbon that is a little de-shielded compared to the other methylene, right? So we run first the broadband decoupled NMR, then we go and run a depth 135, and this is what we get. By looking at these two and by subtracting this spectrum from broadband decoupled spectrum, we can deduce some information. This peak is missing here, so that must be quaternary carbon, that must be that carbon. So we can assign this peak for the quaternary carbon. The missing information of depth 135 tells about one carbon, right? That is quaternary carbon. Then we have negative peaks. This is one here at 40, so this must be CH2, and there is one here which is 20 or so, and that chemical shift can be assigned to methylene. And there are some methynes, methyls. This is methine, this is methine, because methynes are at a different chemical shift than methyls. Methyls are the ones that normally are towards your right hand side. Okay, we have 3 methyls, so we have 1, 2, 3 methyls, and we have 2 methynes. There is one methine here, and there is one methine at this carbon. If you are unsure, you just write down the hydrogens as well on the structure. Then you would know that that's a methine. Okay, so by running a D13 broadband decoupled C13 NMR and a depth 135 NMR and collecting the data would help you to assign the different types of carbon of your compound. That is kind of unequivocal assignment of structures. Otherwise, though you assign by chemical shifts in broadband NMR, you always have that nagging feeling, is it that or this one? Is that the CH2 or the CH, right? That kind of doubt has been taken off by looking at the depth 135 and comparing to the broadband decoupled spectrum. Or you could run the apt once for all, but it takes long time, right? So let's summarize the discussion again here. We have 4 different types of carbons and we have various types of depth. Let's just make a matrix for that. And depth 45, all 3 of them are positive. Only thing is quaternary is missing. What is common to all these 3 techniques is that the quaternary is missing. Depth 135 gives negative peak for methylenes, and methynes and methyls come as positive peaks. In depth 90 you don't see anything else other than methynes. In depth 45 you see all 3 of them. Whatever is attached to hydrogen, whatever the carbon that is attached to hydrogen can be seen in depth 45. So any questions about it? It's pretty easy, right? So this is the C13 NMR of citronellol or carbon NMR of citronellol, and it is a broadband decoupled spectrum, right? And how do we know? Because we can see the CDCl3 here. We don't see the CDCl3 peaks in any of these depth, because CDCl3 does not have hydrogen attached to it, right? Okay. What else? Again, you can count the number of hydrogens, number of carbons, and then you can type different types of carbons. They have quaternary carbon here, I have a quaternary carbon here, and those quaternary carbons could be either of these, or this could be methynes also. So I need to run a depth NMR for this one in order to assign the structure. So if I run the depth NMR, I am missing one of the peaks here. Sorry, that was not a quaternary. I'm sorry, this is a tertiary. Okay, so I only have one quaternary, and that quaternary is here, and that quaternary is gone in the depth 135. So I know that that's a quaternary one. Okay, so whatever is missing is useful. And then this is a positive peak, so that must be methine because of the chemical shift, and because that methine is this methine, or keen methine. Okay, we don't know about this methine, that must be somewhere buried here, right? So that is what, 3, so that is that methine. Okay, and how do we know that? Because there are only 3 methyls, 1, 2, 3. I am leaving those 3 methyls, there is one more peak, that must be methine, because only methine and methyls give the positive peaks, whereas all the negative peaks are methylenes. We have different types of methylenes. This methylene is attached to oxygen, so that is towards downfield, deshielded, and this is allylic, so that must be that. No, I'm wrong here. Why is that so? Okay, anyhow, that's another methylene, that is another methylene, and that's methylene again. So we have 1, 2, 3, 4 methylenes, and those methylenes are seen here. Okay, so depth 135 is pretty informative and pretty useful, right? Okay, if you can understand and appreciate that much information, you're all set. If not, you can look at some more spectra. There is another terpenoid which is called ripsinol, and here we have shown you all sorts of depth NMR and broadband decoupled NMR. This is broadband decoupled NMR, and as you can see here, you don't get any information about different types of carbons. You only get the information about the number of carbons, different types of carbons, chemically non-equivalent carbons. We have about 9 of them as labeled here. 3 of them are methyl. Why is this methyl different than this methyl? Because of any chiral centers. If they are dash stereotopic, they would be different. If they are enantiotopic, they would not be different. I would like to say that there is an element of free rotation here. Let's go with it and see what it looks like at the end of the discussions. Anyhow, you have depth 90 here. In depth 90 we see all of them as positive peaks. Methylenes, methynes, even methyls are all positive. For some reason, not seeing any CH2 here. As to why? I wonder as to why. We'll come back to that. This is depth 135 here. You have two methylenes here, and then there are two peaks that are going down. So in all you have four methylenes. Let's look at the molecule. 1, 2. Where are the other two methylenes? This is the other methylene, and this is one more methylene. So methylenes need not be CH2 like this, which is aliphatic methylene. This is alkenyl type of methylene, right? So this is sp2 methylene, this is sp methylene, and that's the reason. Sorry, this is sp3 methylene. That's the reason why the difference in the chemical shifts. If you see a negative peak around 120, that must be a methylene derived of alkene or part of alkene. These methylenes are part of alkane side chains, right? Anyhow, still it's kind of bothering me. Why are we not seeing any methylenes in depth 90? We just learned in where is the discussion in depth 90. Okay, we don't observe methylene in depth 90. We only see CH, right? Yep, even I am kind of losing the track. Okay, so depth 90 kind of shows us only CH. It doesn't show CH3 and CH2. Depth 45 is the one which has all the three positive peaks. And that means methynes, methyls, methylenes give a positive peak. Excuse me for that confusion. And sometimes confusion helps us clarify some things. So it's not bad confusion, right? Anyhow. So this is a spectrum for this compound. Anyhow, this is the depth 135. As soon as I see this negative and positive peaks, I know that this is depth 135, because no other depth would give you a negative peak, right? So this is depth 135, and this is broadband decoupled spectrum, though it's not explicitly said, because I see something small that is here but that is missing here, so that must be quaternary, and this is going down, so this must be methylene, and it's at 110, so that is that methylene. And there are different types of methylenes depending upon the chemical shift. You can assign those methylenes, and again I am bounced here because I only see two methylenes. I don't see three methylenes. The aliphatic reason here. Anyhow, I just don't know why. Let's see. Look at this one. I just got this spectra from collection of spectra that I downloaded from somewhere. Here it's probably, this is probably the methyl. See, that's where you need more information about NMR, right? These two are going down, so these two are methyls. Maybe one of them is overlapping with the other one. That could be the reason why we don't see three methylenes, and the aliphatic reason, or the structure is wrong. So let's count 1, 2, 3, 4. This is pretty much missing. Could be some solvent, some acetone peak maybe. Okay, anyhow, let's ignore this spectrum and come back to this later on. Let's see what they are assigning to. Where is the other CH2? What is that? CH3 and CH2. Okay, they're overlapping. Why? But still you should be able to see CH2, right? Anyhow, that's pretty controversial spectrum, because if this is a methyl, then we should have one CH2 somewhere. That should be going downwards, right? That's wrong. So we should probably, this is simulated NMR, right? We have two methyls, so those methyls are fine, and this is overlapping. I do understand that, but when you have overlapping, when you run the depth NMR, you should see something going down, because that overlapping doesn't affect the CH2s. CH2s are still there. Anyhow, this is a summary of different types of depths of this compound, which is called codeine. This is the normal NMR, normal broadband C13 decoupled NMR. This is CDCl3. At times, if the solution is dilute, then you see long triplet type of peak here at 77. That is because of the deuterium coupling to the carbon 13 of the CDCl3. Okay, so that's from solvent. You can ignore that safely and count the rest of the things and assign. So I'm kind of clueless as to assign what is corresponding to what, right? So that's when I take the help of depth 135 and depth 45, depth 90. Depth 135 is missing these two, and all of them are missing, so the quaternary is missing in all of them, so we can safely assign these two as quaternary carbons. And there's something missing here, so that must be quaternary, and this is missing, so in all of them, so those four are quaternary carbons, and those carbons are, this is quaternary, 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 okay. So we can assign those four to that four. So, and then if something is not accounting for, that must be, if you add 5 quaternary carbons and if you only have 4 of them here, that means your structure is wrong. Your NMR cannot be wrong, right? So your assignments are wrong, or your structure, whatever you are predicting, is wrong. So you have to come up with a different structure, right? Which can explain the pattern that you see here. That's where the depth would be valuable in identifying the number of quaternary carbons. And in depth 45, all of them are positive, like CH3, CH2s and CHs are all positive. In depth 90, you see only CH. So if I see something in depth 90, and if I don't see in any of the other spectrum, if I don't, if I do see that. So if something is seen in depth 45 and depth 135, and it's also seen in depth 90, that must be CH, right? So all these green ones are CH ones, okay. And okay, there are 1, 2, 3, 4, 5, 6, 7, 8 CHs. So we have to count that. 1, 2, 3, 4, 5, 6, 7, right? And one more, this one, the chiral center, 8. So you got to number them. You cannot just arbitrarily count them. So there are 8 methynes. So that is this codeine compound, and there are 3 methylenes, 1, 2, 3, and all methylenes are in aliphatic region. So that is that methylene, one more methylene, and the other methylene. This is benzylic, so probably I would assign that to that, and this is adjacent to nitrogen, so probably that, and then this H2 is that, okay. And what else do we need to assign here? That's it, right? Methyls, okay. The methyls are the ones which are towards positive side of the depth, and depth 45. So you see something that is positive side, and there is one here. It's pretty overlapping here probably. So there is how many methyls we have? 2 methyls, right? One CH3 and the other CH3. Both are attached to heteroatoms, so they must be somewhere in this region overlapping with each other or a little farther apart. But what is confusing to me here is that in depth 90 they are seen. In depth 90 we shouldn't see them, so they must be overlapping, right? Okay. Anyhow, this is a collection of different types of depth NMRs of this particular ketone. You have 2 methylenes, as you can see in depth 135. You have 1 methyl, as you can see here, positive peak, and there are 3 methynes that are seen here, right? So they are also seen in depth 90. So something is seen in depth 90 as well as positive peaks in depth 135 must be CH, okay. The negative ones are CH2, and these are methyls which are missing from depth 90 on the positive side. Those that are missed from this broadband decoupled spectrum must be quaternary carbons. We have 2 quaternary carbons, so those are missing, and we don't have the broadband decoupled spectrum here, so we don't know what the chemical shift is. But nevertheless, this spectrum confirms that this is the structure, and if you know the molecular formula, you can assign the missing ones to the quaternary carbons. And this is again another slide which shows different types of depths. This is the normal broadband simulated NMR of this compound, It has 4 different types of carbons. This is a stannine, tin metal, and this is attached to this called 4. The 3 of these attached, see in the after the parenthesis, but all those 3 are chemically equivalent. All the 3 butyl groups are chemically equivalent, so we would only see 4 peaks, though the molecular formula would have 12 plus 3, 15 of them, but we would only see 4 plus 1, 5 peaks we would see, and that's what is seen here. I'm recording my lectures. Okay, so this is the normal CH3. That's pretty positive, so it must be attached to silicon, right? It's quite near to 0, right? Shielded. And this is alpha one, which is close to metal, that is beta, and that's gamma, and that is delta. I just don't know why is that so, right? So nevertheless, we were just asked to assign, oh, I know that, because this is methyl, so the methyls have more shielding effects, so they are much towards your right hand side. These are methylenes, so though they are beta and gamma, they are this side, and this is also farther away, so that is deshielded, right? Okay, anyhow, this is normal spectrum, and this is depth 90. In depth 90 you don't see anything, that means we don't have CH, right? And in depth 135 we see 3 of them going downwards, that is negative peaks, so we have 3 methylenes and we have 2 methyls pointing up positive side, so those are 2 methyl groups. Anyhow, this is the summary of all the techniques that we learned today, that is broadband decoupled C13 spectrum. This is APT, this is depth 45, depth 90, depth 135. What is common to all of these? They're all carbon 13 NMRs, just that these are edited NMRs. This is broadband decoupled NMR. And what is not seen here is the off resonance spectrum that we saw, where hydrogens would couple to carbon 13, right? These 4 spectra would give the information that is otherwise missing in the form of off resonance spectroscopy, right? This broadband decoupled spectrum is showing 5 peaks leaving this CDCl3, and in the APT we see one going down, that must be methylene. These are either methyls or methynes, and this is seen here, so that is quaternary. How do I know that's quaternary? Because that is missing in all of these 3 spectra, the depth spectra that is missing, so that must be quaternary. I have one quaternary, and that is coming at 210, so that is ketone carbonyl. And we have a methine that is seen in depth 90, so that carbon can be safely assigned to methine. Now we only have to assign methyls, and those methyls are positive in depth 135, so these 2 are methylenes, because we already assigned this to methine, this to methylene, so we are left with these 2, those 2 are methyls. So that's how the different types of C13 and different types of carbons are assigned in carbon NMR. This is another isomer of the same compound, or is it the same compound? It's the same compound. We pretty much discussed all these things, so I'm going to skip this slide. So to summarize the whole discussion that we had today, is that the number of signals indicates the number of types of carbons in the sample. The symmetry simplifies the NMR, right? Simplifies the carbon 13 NMR. If you have symmetry, you will expect less number of signals, less number of peaks than otherwise. So that's something you have to remember. Chemically distinct, chemically non-equivalent nuclei would give the peaks. The number of peaks is proportional to the number of non-equivalent carbons, or the number of peaks is equals to number of the chemically non-equivalent nuclei, carbon nuclei. The chemical shifts are dependent on the electronegativity of the carbons, which is in turn dependent upon the atoms that are attached to the carbons and the hybridization of the carbons. Okay, we know that sp hybridized is more electronegative than sp2 than sp3. Okay, so the chemical shifts reflect that electronegativity patterns and hybridization patterns. sp3 hybridizations are seen in the first quarter of the C13. Methylenes are sp2 carbons are seen in the second and third quarter of the carbon 13 NMR, and you would see quaternary carbons that are on the fourth quarter of carbon 13. If you were to divide into 4 quarters, you can respectively assign the quarters to different types of hybridizations. Quaternary and ipsocarbons would be smaller because of their relaxation times, which are much higher, and they can be differentiated using edited carbon 13 NMRs. Okay, like apt and depth would help you to gain the information as to whether the given carbons are primary, secondary, and tertiary and quaternary. Even depth would tell you whether if the carbon is quaternary, because they would run a broadband NMR first and then go for depth and then subtract one from the other, and you would see the missing one, that is quaternary or ipsocarbon. Okay, that summarizes the discussions of edited NMRs, and these are all edited C13 NMRs. These are all some of the examples and some of the problems. You can just solve them. How many peaks would you expect there to be in the carbon 13 NMR of butane? It has symmetry, so you would expect 2. How many you would expect in the isomer, that is methyl propane? You would expect you have to draw this structure soft. Don't go by this linear formula. If you go by this linear formula, you would be doomed. You have to translate that into the skeletal formula, and if possible into 3-dimensional drawings, then you would be safe. Okay, butanol, again you have to draw it out so that you can see that it has a carbonyl, and that will have a carbonyl peak at 200 or so, and then you have 3 different types, so you have to assign. Then you can simulate the NMRs. If you know the range of the chemical shifts, you can pretty much draw the NMR diagram, because sketching the carbon NMR is much easier because everything is a singlet, right? Because at least in the broadband decoupled NMR, when we say carbon NMR, we normally refer to the broadband decoupled spectrum. Okay, so we don't quite expect you to do the hydrogen coupling and show it as a triplet or a doublet or a quartet, right? So that's something you should keep in mind. Nowadays we don't even run those kind of spectra because we have depths and apts, right? Anyhow, how many peaks do you expect for cyclohexane? Only 1. How many peaks do you expect for this? You have to count and look at them, right? So you have to ask pretty much the same question every time. Is this carbon unique, or is it something similar to the other carbon? Is this methyl different than that methyl? Then though they are methyls, they would give 2 different peaks. Very rarely you see the overlap in carbon 13 NMR. Okay, so that's the summary of what we had in the previous slide. Can you identify the isomers of this compound? By looking at the formula, you know that there is an oxygen. The first step would be to calculate the degrees of unsaturation and see if there is a ring or a double bond or an unsaturation in some other form, and then draw all the isomers, possible isomers for this, and then count the number of carbons and look at these carbon NMRs and then assign them, right? So for example, there is a chemical shift of this peak at 200, whereas this chemical shift is much higher, like 210 or so. So this must be a different isomer than this one, and so you should be able to differentiate between this isomer and this isomer, because this particular isomer has 3 different types of peaks in the aliphatic region. This only has 2. So can you all draw the isomers and find out? Yes, we should be able to do that. Here is what it's shown. Butanol, if you draw the structure out, let me try if I can draw that, has okay, bear with my drawing. It's not as I would draw on a board, because I'm trying to use the mouse and then draw it on a computer screen, and it's pretty skewed. Okay, so that's the aldehyde one. So there is, out of these 3, the chemical shifts of all these 3. Okay, the mouse is gone now. Okay, let's see if I have the pointer somewhere. Okay, this has a different chemical shift than this one and then this one, so this must be the aldehyde one, right? So these 2 are ketones. Oh no, this is also an aldehyde. So then it boils down to aliphatic region. Sometimes then substituents and the types of substituents affect the chemical shifts of the carbonyls. If it has 2-methyl propanol, that would be like this one, and that's an aldehyde. But this alkyl group has a different additive effect on this chemical shift of this carbonyl than this alkyl group, and that's one of the reasons why there is slight difference in the chemical shifts of these two carbonyls. Okay, so now we have to look at this methyl and this methyl and say there are only two methyls and there's one methine, but this methine is chemically different than these methyls. These methyls are chemically equivalent because it's the same as this one, so they would give one peak and this is giving other peak, so this has two peaks here, so I would say this is for this compound, right? So then this compound is this one. How would you know that? You have to draw the structure out. 2-butanone, that is the carbonyl is at the 2 carbon, and it cannot be a terminal, right? Because ketone by very definition should have 2 alkyl groups. So 1, 2, 3, 4, and this is what is giving that peak, right? And it has 3 different types of carbons, so you have 3 peaks on the aliphatic region. And if you have a depth for this compound, that is 2-methylpropanol, you would be able to assign the structure much more unequivocally, because you would see methine carbon differently than methyls. Let's say if you run a depth 90, you would see only CH peak, right? Anyhow, let's move to the next one. So these are all the summary points. I'm not going to read through all of them, but you should be able to get the discussions by looking at that. Anyhow, I'm not going to talk about 2D NMR because it's kind of advanced. I use these slides for my advanced spectroscopy class, so I do have this in case somebody wants, they can look at these techniques. This PowerPoint is made available on my courses, so you can download, you can print, you can follow these lectures online, and we would solve the problems when you come back on Monday. Okay, thank you. Have a nice evening. Bye.